Hello. We're going to solve a problem, an open steady problem involving a flow through a boiler tube. As water flows through the tube, is being heated by electrical heating in three different sections. In the first section, the water goes from 30 degrees Celsius to saturated liquid at state 2. Then it's heated even more to saturated vapor at state 3. And finally, it's heated to a superheated vapor to state 4. So we have to find the electrical work transfers. Also, if we do not use the PC model, suppose we use the SL or PG model, we want to see how the answer differs. Okay, so we begin just by first figuring out how the states should look on a TS diagram. Of course, the pressure is not dropping. Pressure remains constant in this problem, so we know that the TS diagram is very simple. It's a single constant pressure line at 100 kPa line at 30 degrees Celsius. This must be 100 degrees Celsius. At 30 degrees Celsius, we have a state 1, which is subcooled. State 2 is saturated liquid, state 3 saturated vapor, and state 4 would be the superheated vapor, the final state of the steam. Okay, so let's launch the TESTcalc and evaluate the state first. But which TESTcalc should we launch? Obviously, we'll go after system analysis. And we have an open system. We have an open steady system because the pipe is working in a steady state. And then we'll select generic because specific is designed for special purpose systems. So you follow the generic systems, then you will see we'll reach the single flow system would be our destination because one flow in and one flow out. That's what is going on. And let's launch the PC model. And finally, to go to the TESTcalc, we go here, run. There we go. So H2O is already our fluid. Let's evaluate state 1, 100 kPa. Mass flow rate is, and the temperature is given 30 degrees Celsius, and the mass flow rate is 1 kg per second. State 2, pressure didn't change. Of course, mass flow rate is the same. Notice how I'm using the equations. And how do you specify saturated liquid? The answer is quality. We'll put quality to be 0. State 2 is done. State 3, again, we have pressure doesn't change. And mass flow rate remain constant. But the quality is now saturated vapor, so 1. Finally, we have state 4. Where the temperature is known to be 200 degrees Celsius and the pressure is, of course, unchanged. So we calculated all the states just to make sure what we expected and what we found are the same. Notice if you draw a constant pressure line, this is what we thought, 1, 2, 3, 4. Well, we thought the state 1 will be somewhere here, but generally state 1 falls almost on the saturation line. The difference of subcooled liquid and saturated liquid is so little on the diagram. Okay, now let's go and analyze the devices. We'll call device A meaning the section 1, which means state 1 to state 2. And there is, of course, the heat transfer. It's insulated. And bingo, we find the external work transfer to be negative 291. Of course, external work has sign involved. And if we win hip, work in is negative, so that says work is going in, 291 kilowatt in the first section. Second section, we have state 2 going to 3. Again, putting Q dot to 0, we find the W dot external. And finally, in state C, the device C stands for, we go from state 3 to state 4. The superheating section, Q dot equals 0. And there we go, we found W dot external. But notice also that we also found entropy generation in each section. You can go back and see that there's a lot of entropy generation in the second section when water boils. And if you want to find what is the total entropy generation, what is the total external work transfer in the entire system, instead of adding, we could just add all these sections up. Another way could be to treat it as a new device, device D, where state 1 is my inlet and state 4 is my exit. No heat transfer, and that will produce the total heat transfer. So in other words, to heat up the water, we need 2749 kilowatt of electrical power. And notice that bulk of it is required in boiling the water from liquid to vapor. Heating the liquid and heating the superheated vapor takes considerably less amount of energy in this case. Okay, so now suppose we want to find one of the part, I think part D says, what if for device A, the first section, you use the SL model. If I want to use the SL model, so remember the PC model answer is minus 291. Let me write those down. So the different section that we got, the answer that we got, W dot in section A using PC model, we got 291 kilowatt. W dot in C, we got 199 kilowatt. This is also PC model. And W dot in B, which was the largest, 2258 kilowatt. Now we are going to repeat this and this with different models. So our goal is to find W dot in A if we use the PG model. So for that, we go there and we launch the PG model. Again, we go to the same destination, single flow systems, and this time launch the SL model for the first section. And we select water, liquid water as our system, working fluid. State 100 kPa, temperature is 30 degrees Celsius. M dot is 1. We are neglecting kPe, so we don't bother with that. Equals P1, and the temperature we know becomes 100 degrees Celsius. There is no quality in case of solid liquid models. We must apply the temperature. And now that we found the states 1 to 2, Q dot equals 0, and we get minus 292.88, minus 293. Not bad. So W dot in is 2. This is quite close. The PG model answer is quite close to the PC model answer, as you can see. So when you model liquid, generally SL model is pretty good as the PC model in most situations. Now what do you think about when we superheat the vapor? Vapor is kind of like a gas. Well, from 3 to 4, can we treat it as a gas? That's the question. So what we are going to do, this was SL model answer. I was totally wrong there. So W dot in for the part C, now we want to use the PG model. The question is, if I use the PG model from 3 to 4, how much energy is added? So for that, we're going to go launch the, again, single flow system, but this time we'll launch the PG TESTcalc. And we'll select H2O as our gas. Okay, 100 kPa. And it was 100 degrees Celsius, if you remember, which is, okay, mass flow rate is 1. Pressure doesn't change and temperature became 200 degrees Celsius. Mass flow rate is still same. Now if you go to the device panel and set it up, inlet and exit, no heat transfer, and bingo, we get minus 188 approximately. So you get 188 kilowatt. It's not as good as the PC model, but not bad either. So the idea that what is a gas? The farther you go from this dome, far away, the more superheated the vapor is, the more it acts like a gas. So in other words, from 3 to 4, our answer is 188. Suppose we heat it from 4 to 5, say another 200 degrees Celsius rise, and if you find how much energy is needed for that, I can guarantee you that the PC model and the PG model will be much closer this time. So we'll stop here, and I would ask you to go and explore the entropy generation, which is produced as part of the results. And you can do parametric study quite easily by just simply changing anything and clicking the super calculate button. So I'll stop here and let you explore this test calc.